Today's topic for the session is probability. What is probability? In general, we call probability as a chance. Probability is said to be a chance of happening and not happening. So what do you mean by happening and not happening? Let's see with one of the small activity, because we see in many international cricket matches there's a tossing of a coin through which they decide on the batting or the bowling. So this has a lot of probability which can be applied for tossing of a coin to decide on the winning side of the country which takes the batting or the bowling initially. We are very enthusiastic to know which country, if India and Pakistan plays the match, we are very enthusiastic to know whether India is batting first or it is bowling first. And that is purely decided on tossing of a coin. Now, what is the rule of tossing of a coin in international cricket matches? Let's see through a coin. Now, I have a coin in which I have heads in one side of the coin, and then on the other side I have tails. Usually this three-headed lion is called heads, and the other side of obviously is called a tail. Now coming to this, the tail and the heads is what is the coin, with heads and tails. Now this once again with tail and once again with heads of this 10 rupee coin which I'm going to show. Now I want to know whether I get heads or tails if I just toss this coin. I say it is heads, and yes, it is heads. It is heads. It is. And then because I got heads, I'm happy that I'm going to choose on whether I'm going to bowl or bat depending on the weather conditions and the pitch conditions. Now this question of whether I'm going to get a head or a tail is the biggest question in mathematics. When I toss, I got a head, but when I toss, I may get a tail. This time I got a tail. This time is a tail. Now I got a head in the previous case and I got a tail in the second case of tossing of a coin, which makes me puzzled or think of on when can I get a tail or when can I get a head is the biggest question which connects probability, indirectly called the chance. So the chance of getting a tail or chance of not getting a tail is how we judge on probability. So to start with, the head and tail we have seen in tossing of a coin. Let's come back with some mathematical understanding. Now in this tossing of a coin, I can either get a head or I can get a tail. So there are 50-50% chances of getting a head or a tail because there are two possibilities. One is the head and one is the tail, out of which there are 50% chances of getting a head and 50% chances of getting a tail. How do you know that there are 50% chances? Is the biggest question here. Because when you toss a coin, there are equally chances of getting a head or a tail out of the 100% of possibility. So this kind of questions are arising due to the probability which we need to estimate through mathematics. So let's see through many further examples on how we can estimate the chances of happening or not happening through probability connected with mathematics. Now let's take one more example to understand probability more better. So for example, I have two possibilities with bag 1 and bag 2. In both of the bags, I have say different colored balls, in which in this bag I have so totally I observe that in this bag there are 1, 2, 3, 4, 5, 6 balls, assuming that these are the balls inside the bag. And in this bag there are 1, 2, 3, 4, 5, 6 balls even in bag 2. But here there are 5 balls which are red in color and 1 ball which is blue in color. But in this case there are 2 balls which are red in color, 2 balls which are blue in color, and 1 ball which is white in color, or 2 balls which are white in color. So if I see the comparison between bag 1 and bag 2, my question is, what is the chance? The question here is, what is the chance of picking up a red ball from each of the bags is the question out here, through which we understand the probability or chance of happening more better. So with the question being, what is the chance of picking up a red ball from each of the bags, we have the bag 1 clearly with 5 red balls and 1 blue ball, and here this bag with 6 balls being 2 with red, 2 with blue, and 2 with white. Now the question being, what is the chance of picking up a red ball from each of the bags? I think this bag has more chances of picking up the red ball because there are 5 red balls and only 1 blue ball. So chances of picking a red ball is more here. And the chances of picking the red ball is not that high because equally all the different balls are of same color. Equal number of balls are of different colors, where 2 red, 2 blue, and 2 white may not be a higher chance of picking up a red ball from the bag. But this bag with 5 red balls, the chances of picking up a red ball is more high in this case and less of in this. This makes us understand that situations differ, then the chances of happening and not happening differ. In the case of bag 1, chances is more of picking a red ball, and in bag 2, chances are less of picking a red ball. Simply because there are more number of red balls in this bag and there are less number of red balls in the bag, is how we understand. So the answer for this question is obviously bag 1. This is the answer. Bag 1 is the answer. So this is how we understand probability in daily life connected with many problems. But what is the exact definition or the exact formula through which we can identify the probability or chance of happening and not happening using the real life situational problems is what we are going to discuss for the session. Probability connected with the formulae. Now let's see the types of probability. Now here we have 2 different types of probability which differs between the experimental probability and the theoretical probability. So let's see each of them, the different types of probability. Experimental and theoretical probabilities. Now, as the names itself define clearly, experimental and theoretical clearly makes us understand that the initial probability, which is called experimental probability, is conducted through an experiment. This is through an experiment. Now, to come with this experiment, I identify that different experiments give different values of probability. Say, for example, one of the French mathematician by name Buffon has tossed the coin 4,440 times. If I toss a coin 4040 times, he could get 2048 heads. Out of this, he got 2048 heads. So this is purely an experimental probability because an experiment was conducted in attempting on tossing a coin 4040 times. And then he could get totally on the whole when counted 2048 heads and the rest were all tails. So he calculated on the chances of getting the heads through this experiment counting up to 4040 times of tossing of a coin. So clearly he just did, he got the probability as simply 4040 times which he has attempted, out of which he got 2048 heads. When divided, it gave the value approximately the value as 0.507. So this was the value as obtained for an experiment which had 4040 times of tossing of a coin. Now what happens if this number is increased? If I increase up to 10,000 times of tossing of a coin, then definitely the number of heads also change the outcome which we cannot predict. Then when this was divided with this, then this divided with this, then approximately gives the value 0.5 etc., but it may not give exactly the value. So such kind of experiments through which we identify the percentage of chances of happening and not happening is called experimental probability. The process of experimenting by tossing number of times and then finding each of the results is called experimental probability. Now what is theoretical probability? Theoretical probability is not done through an experiment of so many times of tossing a coin, but we assume that when I toss a coin, the possibility is, when tossing a coin, the possibility is either getting a head or a tail, where two sides of a coin will give me one head out of two sides and one tail out of two sides. So these are the chances of happening, getting a head or a tail, is how we understand the theoretical probability. The possibility of getting a head is 0.5 because one head out of one head and tail, which is 2, and one tail out of this with this, so that I get one head out of head and tail is two sides, which gives me 2, and one head is one of the head which are right here. Similarly, one tail out of one head and one tail is what I get for this. So my experimental probability of the same coin when it is tossed 4040 times gave me 2048 heads, makes me understand that the probability is 0.507 through the experimental probability, and the theoretical probability makes us understand that one head out of two possibilities and one tail out of two possibilities gives me 0.5, which is based on the theoretical probability. This is how we differentiate between the theoretical and the experimental probability, the types of probabilities which we have discussed out here. So let's see the theoretical probability in brief, because most of the problems in the session are related to theoretical probability, and hence finding the chance of happening and not happening through theoretical probability. So theoretical probability, as we have defined in the previous session, has its own definition in the formula which we're going to take here. So let me take first initially the event E, which I'm going to conduct. Let E be the event. Now the event depends on the situation of the problem. Tossing of a coin is one of the event, or playing of a game on the dice, throwing of a dice is one of the event, or picking up a ball from the bag is also one of the event. So different problems have different situations which hence define the events. So in general, let E be the event which I'm going to find. Then in this case, my probability of happening of an event E is given by So probability of happening of an event E can be anything, is given by the symbol P of E, generally denoted as probability of happening of an event E, is given by the formula number of trials in which the event happens, number of trials in which the event happen by total number of trials. So this is how we define the probability of an event in mathematical formulae. So probability of an event E is number of trials in which the event happened by total number of trials. So let's see how we can use this formula for an example problem. Say tossing of a coin, as I have taken. For tossing of a coin, I got the total number of events. In the event of tossing of a coin, the probability of getting a head, if that is the event, then that is total number of trials is either getting a head or a tail, being two possibilities, and number of trials in which the event happened or getting of a head is one possibility. Therefore, for this, using the formula, I get probability of head, getting a head is 1 by 2, is how we understand. So let's see more examples to understand this formula more better. To start with, one of the example problem connecting with the formula. Now let's come with the more modified definition of probability as dedicated to one of the mathematician called Simon Laplace. So there are many mathematicians who have come up with different modifications on definition of probability, but the most accurate definition we are going to take now is the probability of occurring of an event E is given by, denoted with P of E, is number of outcomes favorable to event E by total number of possible outcomes. Is how we come out with the most modified definition of probability, the theoretical probability of happening of an event E or occurring of an event E, given by number of outcomes favorable to event E by total number of possible outcomes. Let's see an example problem connected with understanding the probability through the mathematical formula. So what is sample space? Sample space is very important before we start with the problems of probability using the mathematical formula as defined in the recent session. Now before we start with the problems, sample space has its own definition. What is sample space? The definition says set of all possible outcomes of an event E is called the sample space. Say for example, we all know what a dice is. Usually we use this dice in playing a game where you have one dot and then we have two dots and then we have three dots or 4, 5, 6, etc. So in this dice, I have totally set of all possible outcomes when I throw a die is I may get a 1 on the top, a 2 on the top, a 3 on the top, a 4, 5, 6, anything on the top. But I cannot get a 7 at the most on the top. Therefore, the set of all possible outcomes of the event E, here being throwing of a dice while playing a game, is the event E here. Let's see what are the possible outcomes. The sample space, denoted by generally S, for this particular problem is nothing but the first possibility is I may get a 1, and then I may get a 2, 3, 4, 5, or a 6 when I throw a die. So when I throw a die, sample space is 1 to 6. So here this is throwing of a dice. Say I take one more example, tossing of a coin, which we have done. So when I take a coin, and this coin, when I toss it, I have heads, and then the other side we have tails. Therefore, when I toss this, the event here is tossing of a coin. Therefore, my sample space is either getting a head or a tail, because the top can be either head or tail is what is the sample space here. In this problem, the sample space is this. Is how we understand the sample space is the set of all possible outcomes of an event A. For dice being the possible outcomes is 1 to 6, and for a coin being the possible outcomes are either head or a tail. So using the formula of probability of E, of event E, let's see some of the problems. But before that, the probability of occurring of an event E is given by number of events favorable to event E by total number of outcomes, which is sample space. Therefore, this is the formula of the probability of event E is N of E by N of S is what we use to see how we can use the probability. Say, for example, the question is, what is the percentage of chances of getting a 6 on the top when a dice is rolled? So this is the question which we have. Now we know that we have already seen a dice which is rolled or thrown in the game. Then in that case, we see that we may get a 1, a 2, or a 3, 4, 5, or a 6 on the top. So the question here exclusively is about finding the percentage of chances of getting a 6 on the top when a dice is rolled. Now the word chance does immediately make us understand that it is the probability which we need to find, because probability is the chance of happening and not happening. So with the question on finding the percentage of chances of getting a 6 on the top when a dice is rolled, let me take a dice on which I need to get a 6 on the top. So I need to get is how I have the dice on which I need to get a 6 on the top. Therefore, connecting this, my event E here is very important to be identified. The first thing I need to do is identify the event E in the given problem. So for this given problem, my event E is rolling of a dice, because dice is rolled, the event is rolling of a dice in this case. Now with this, I clearly have getting of 6 is the number of events which are favorable to event E, because my target is to get a 6 on the top. That is, my number of targets are 1, that is 6. Therefore, N of E is 1. Number of events, outcomes favorable to the event E is the outcome 6, which is only 1. Therefore, N of E is 1. Now, total number of outcomes, which is the sample space S, because we know that the sample space for this is clearly 1, 2, 3, 4, 5 and 6. So therefore my sample space being 1 to 6 clearly has 1, 2, 3, 4, 5, 6. Total number of outcomes is 6. Each of the phase, the top can be either 1 to 6. Therefore my n of s is 6 is how I understand. Now n of e is 1 and n of s is 6. Using the formula, I have my n of p. P of e is n of e by n of s, which gives me n of e is clearly 1 over 6. Therefore, the probability of getting a 6 on the top is 1 over 6 is what I get. That is, the probability of getting a 6 on the top is 1 over 6. But the question is about percentage of probability or percentage of chances of getting a 6. Therefore, percentage of chances of getting a 6 on the top when a dice is rolled is simply P of E times 100. The percentage is calculated by multiplying the probability with 100. Probability times 100 gives us the percentage of chances. Therefore, using this formula of P of E times 100 for finding the percentage of chances of getting a 6 on the top when a dice is rolled, I simply get P of E times 100, where P of E is 1 over 6. Therefore, in place of P of E, I substitute 1 over 6. That is 100 by 6, which is approximately 6 ones 6, 40, 6 6 36.66, etc., which is approximately 16.7%. So I understand that there are only 16% or 17% chances or 16.7% chances of getting a 6 on the top when a dice is rolled, not a better chance. 16% is a very less chances of getting a success out of when a dice is rolled, is how I understand with the least of the 16%. So let's see how I can compare the chances with the same example as I considered with a bag containing the different colored balls. So let's recap with the previously done problem and then identify on how we can compare the two chances or the two probabilities. Say for example, I take the two examples, reconsider the two examples as I have taken here with the bag, one which contains 6 balls, and this bag 2 also which contains 6 balls, where here there are 1 blue ball and 5 red balls, and in this case 2 blue, 2 red and 2 white is what we have taken in the previous case, this being bag 1 and this being bag 2. Now in this, let's compare the two chances where is the better chance of picking a red ball. So if I wanted to find the probability of picking a red ball, where the event in this case is picking up a red ball, picking up a red ball is the event out here, then we see that the event of picking the red ball is n of e, that is the number of outcomes I can get out of the red balls is that I can pick 5 different red balls and the total number of outcomes are 6, as clearly seen here. Now in this case, let me say for this it is event E1 for bag 1 and this is for bag 2. Then here the total number of outcomes of picking the red ball is that I can pick 2 red balls out of the total number of balls, which is 6, is what I get further as 1 by 3. Now let's see the percentage of chances. Now percentage of chances is P of E times 100, as we have already seen. So this multiplied with 100 will give me 2 3s and 2 5s. So this is 5 5s, 25 by 3, that is 3 8s, 24, and 10, 3 3s, 0.3% is what I get here approximately. So here the percentage of chances is 83.3% of picking a red ball. Let's see how much is the percentage of chances, how much are the percentage of chances of picking a red ball from the bag 2. So in this case, my percentage of chances of picking the red ball is 1 over 3 times 100, because 1 over 3 is the probability as obtained. I get this to be 33.3%. Now where do you think there is a higher chance of picking a red ball? The percentage of picking is just 33% approximately, and the percentage is 83%. It is a good percent to pick the red ball, is how we understand in comparison of chances. So picking up a red ball which contains 5 red balls and 1 blue ball in the bag is more chances are more higher than picking a red ball from a bag containing 2 blue, 2 red and 2 white balls, in comparison of estimating the percentage of chances of 2 different conditions or situations. So elementary event. So what is an elementary event? So let's see an elementary event with its own definition and a few of the examples. So elementary event is an event which has only one outcome, is called an elementary event. For example, picking a red ball from a bag containing 6 balls where 2 red, 1 blue and 3 white balls. So in this bag containing 6 balls, there are 2 red, 1 blue and 3 white balls, where picking a red ball from a bag is an event which has only one outcome, that is picking only the red ball. So the outcome here is a red ball, in which we call as elementary events. So this is one of the examples through which we understand the elementary events. Say for example, I take a dice, and in this dice I want to get getting a value less than 3 on its top, that is on the top of the surface of the dice, is not an elementary event, because if I want to get a value which is less than 3 on its top, the possibility is I may get a 1 or a 2, not a 3, because less than 3. So the possibilities are I may get a 1 and 2, which is not, that implies more than one outcome. So in case of these kind of problems, the outcomes are more than 1, where I have 1 and 2. So more than one outcome, and hence getting a value less than 3 on its top is not an elementary event. So this is not an elementary event. So like this, we understand the difference through identifying the number of outcomes in the event or the conducting of the event. So picking a red ball from a bag is purely an elementary event because there's only one outcome of picking up only the red ball. For getting a value less than 3 on the top of the dice is not an elementary event because we can get two values, either 1 or 2, when I say less than 3. So there are two outcomes which makes us contradict the definition, and hence throwing of a dice and getting a value less than 3 on its top is not an elementary event. Two outcomes, 1 and 2, is how we understand the elementary events. So let's see what is the mathematical relation in identifying the relation between each of the elementary events mathematically. Let's construct this and understand this more better through an example problem. So to start with an example problem, let me consider a bag which contains totally 8 balls. So this bag totally contains 8 balls, out of which 5 are blue, 2 are yellow, and 1 is white. So these 8 balls have 5 balls which are blue in color, 2 are yellow in color, and 1 is white in color. Now I have 3 possibilities where I want to find the probability of each of the color. Say for example, in the initial case, I want to find the probability of getting a blue color when I pick the ball from the bag containing 8 balls. So clearly, probability of picking the blue ball is total number of balls, which are 8 in number, and the number of blue balls, which are 5, which comes here. That is, the number of outcomes is number of blue balls which I can pick, which is 5, and the denominator is total number of outcomes, that is totally 8 balls which come in the denominator. Similarly, the probability of picking a yellow ball, let me see what is the outcome. Totally, there are 8 balls, out of which I can pick 2 yellow balls. Therefore, this comes out to be 2 over 8. Thirdly, the probability of picking a white ball from the whole bag is 8 on the bottom, and then there's only 1 ball which is white which I can pick, the outcome being 1. The number of outcomes favorable to the event E of picking a white ball is 1 over 8. So each of the elementary events here are identified as picking a blue ball, picking a yellow ball, and picking a white ball. So for these 3 elementary events, let's see what is the mathematical relation connecting the elementary events. Interestingly, as I see these 3 values, I just try to add them and see what is the outcome. So when I add each of the values of the 3 elementary events, I get 5 over 8 plus 2 over 8 plus 1 over 8, which on simplification gives me 8 times. So on this consideration, I get 8 as the LCM, and then I get 5 plus 2 plus 1. This on further simplification gives me 8, 5, 6, 7, and 8. Therefore, this gives 1. So what does this make us understand? This experiment or this example problem makes us understand that sum of all the probabilities of elementary events is always equal to 1. So I come to the conclusion that in this case of the problem, which is universally true for any of the problem which is taken with elementary events, I finally conclude that sum of all probabilities of the elementary events of an event E is always equal to 1, is how we conclude the formula. Sum of all probabilities of the elementary events of an event E is always 1. So sum of all the probabilities of elementary events is unique, is how we understand the uniqueness of the probability connected with elementary events. The mathematical relation out here. So let's see what are complementary events and their respective probabilities. Complementary events are the events which are quite opposite to each other. That is, getting of a head when I toss a coin, then its complementary event is getting of a tail, because the other side of not getting a head is how we understand the complementary events. So here I identify the complementary events through occurring and non-occurring, or happening and non-happening, happening and non-happening of an event E. So this is how we differentiate between happening plus non-happening, is how we understand the complementary events. They are said to be complementary to each other. Say for example, I take probability of getting a head when a coin is tossed is 1/2, then the probability of getting a tail when a coin is tossed is also 1/2, but I can say this is 1 minus probability of getting a head. We identify the complementary as 1 minus probability of getting a head, which is found to be half. That is, I get 1 minus half, which is 1/2, is how I get probability of getting a head and T. So here these two are complementary events. Therefore, if A and B are complementary events, probability of A plus probability of B is 1. So this makes me conclude, that implies probability of H plus probability of T is 1 in case of tossing of a coin. For tossing of a coin. Therefore, for any two events, complementary events are defined as, for two events A and B, I have P of A plus P of B is equal to 1. Then I say A and B are complementary events. Therefore, for complementary events, P of A plus P of B is always equal to 1. So when I say the two events are complementary, then this has to come in mind as the mathematical formula. So generally, the complementary events are denoted with general notation as in the following manner. Say for example, I say occurring of an event E is denoted with E, then I say non-occurring of an event I denote with E bar or E complement. Then in this case, E and E dash are complementary events. That is, E and E bar are complementary events. Therefore, I have the formula P of E equals P of E plus P of E bar equals 1. That is, P of E bar is more taken as 1 minus P of E. To read in words, probability of occurring of an not occurring of an event is 1 minus probability of occurring of an event, is how we understand this mathematical formula connected with the probability. So there are two types of special events which we identify in the topic of probability. The two special events which we are going to discuss exclusively in the session are impossible events and certain events. So these are the two types of events which are called as special or trivial events. So these are called even trivial events. Now, what is special about impossible events? That is, when I take a situational problem, if there is impossibility, if it is impossible to find the probability, then we call that as impossible or the certain. Let's understand the definitions through the more exclusive examples. So here, imagine I take a bag containing 6 balls, out of which there are 2 red balls, 1 white ball, and 3 blue balls. Now in this case, the probability of picking a yellow ball out of this bag is impossible because however you search, you don't have a yellow ball inside the bag. You have 2 red, 1 white, and 3 blue. So this probability of picking a yellow ball is almost impossible. So picking of a yellow ball is 0 since the bag doesn't contain a yellow ball. Therefore, these kind of events are called impossible events where the situation goes totally out of possibility. Picking a yellow ball is being one of the case in this example problem. Therefore, usually for impossible events, P of E is 0, then we say the event E is impossible event. So for impossible events, P of E is 0 implies E is impossible event. So for impossible event, we have P of E equals 0. So let's see what is a certain event with a similar example. Say I have a bag containing there are 6 yellow balls inside the bag. All 6 balls are yellow in color. There's no other ball which is different colored in the bag. That means if I wanted to find the probability of picking a yellow ball, so every time you pick a ball blindly from the bag, you get certainly a yellow ball. You cannot get any other color because the only existing colored balls inside the bag are yellow. So probability of picking a yellow ball is certain, therefore it is always 1. In this case, we say the event is certain because however number of times you pick the ball, it is always yellow in color. So probability of picking up the yellow ball is 1. So in such cases, we have, since the bag contains all yellow balls, unlike the previous case where the bag doesn't contain a yellow ball at all. So in this case, I have P of E equal to 1 implies E is certain event, is how we understand the difference between the impossible and certain events. P of E equal to 0 implies E is impossible event mathematically. P of E equal to 1 implies E is certain event with their own respective mathematical formulae. So the certain event here is also referred sometimes as the sure event because it is sure to happen. We call that as a certain or a sure event if P of E is 1, is how we understand the 2 special events in probability. Now in the session, let's see the range of probability. We need to understand the range of probability in understanding the values through their general understanding of probability. So let's recap with the definition of probability. To start with, we have for any event E, we have probability of E is NE by NS, and NE is number of outcomes favorable to the event E, and N of S is total number of possible outcomes. Therefore, we see that in this case, at the most, N of E is always less than, at the most being equal to NS. We see that this is less than or equal to this clearly. That implies N of E by N of S is always less than or equal to 1. That implies n of e by n of s, which I brought to the left, is nothing but p, which I'm going to substitute in terms of this. So this being p of e is always less than or equal to 1. Also, I identify that probability cannot be negative. So at the most, p of e is greater than or equal to 0, since chance cannot be negative. The chance of tossing of a coin cannot be negative, because we can understand that through the general understanding of the probability or the chance of happening and not happening. Therefore, p of e is always greater than or equal to 0, and this is less than or equal to 0. Therefore, connecting both of them, I have 0 less than or equal to pe less than or equal to 1 is what I get as the range of the probability always lies between 0 and 1. It does not cross 1 on the right or does not cross 0 on the left. Therefore, if I take it on the number line, I have the probability which lies between this, including 0 and 1. So probability of E always lies between 0 and 1, inclusive between. It doesn't lie outside of 0 and 1. Less than 0 or greater than 1 is how we understand the range of probability. At the most, here I get impossible event, because p of e is 0 at this point, and at the most it is 1 if it is a certain or a sure event, is how we understand the range of probability. Impossible event and certain event and the range of p is how we understand through the basic definition of probability as NE by NS. So now that we have discussed about the probability and few of the example problems connecting the definition of probability, let's see the learning outcome of what we have learnt about. Now we have seen different probabilities, the different situations or the different events gave us the different values of probability. Now let's come back to the question on why the international cricket matches use tossing of a coin for deciding on the batting or the fielding, the bowling decision, which is taken generally by tossing a coin. Why is it that tossing of a coin is taken as the chance of deciding which team wins and which team loses? To identify this, let's come with tossing of a coin and see why it is used through a more mathematical, valid understanding and justification. When I toss a coin, I have seen clearly in my previous activity of tossing a coin, initially I got the head, and in the second chances I got the tail. So my probability when the event is tossing of a coin, then probability of getting a head was 1 chance out of 2, and my probability of getting a tail is 1 chance out of 2 equally. That is, in this case, the percentage of chances is half times 100, which is 50%, and in this case also I get percentage of chances is half times 100, which I get to be 50%. So the winning and losing or getting ahead and not getting ahead has equal chances in case of tossing of a coin. And because of the equal chances of either teams winning on getting a head or a tail, or winning on deciding on the batting or the fielding session, is decided on equal chances, and hence the international cricket matches decide on tossing a coin for deciding on whether the team wins or loses through equal chances. So this has come because of the equal chances is the answer. So this is one of the learning outcome, or there are many learning outcomes through which we can estimate things through the probability connected with mathematics or daily life. Now let's take this example problem of playing of a cards. We all know the rules in the playing cards, where there are totally 52 cards on the whole in the playing cards. Now this question is about drawing an ace from the 52 cards, a well shuffled pack of 52 cards. I need to pick an ace, and we need to know the probability of picking an ace and not an ace for this given problem. So let's see how probability can be applied in real life now that we have learned all the topics of probability. Now coming to this, initially we need to identify the event E. The first thing we need to do in case of these word problems is identify the event E. As clearly seen here, we have that it is about finding the probability that the card is an ace, then my event E is picking up an ace, is how I understand the event E. Now total number of cards usually we know are 52 in number. Now in the entire 52 cards, I know that number of aces are 4, is the knowledge I need to have in the playing cards. Therefore, the number of aces is 4 and total number of cards is 52, then picking up an ace, which is probability of E, is total number of outcomes are 52, because I can pick any card out of 52 cards in 52 different ways, or 52 times I can pick the card out of all the playing cards. Therefore, total number of outcomes is 52, and number of outcomes of getting an ace is 4, because total number of aces is 4, which I can pick on the whole from 52 cards. So therefore, because event is picking an ace, there are 4 outcomes of getting an ace, is how I understand the probability. This clearly gets cancelled to be 1 over 13. Therefore, probability of getting an ace is 1 over 13. It's quite simple. That implies probability of getting an ace is 1 over 13, is how I understand this problem. Secondly, my question is about what is the probability of not getting an ace. And this question makes me understand or recollect on the complementary events which we have discussed in the recent sessions. Because happening and not happening, or occurring and not occurring, are always connected through the complementary events, where P of getting an ace and probability of not getting an ace, the sum is always 1, the definition of complementary angles. So let's see how we can find the probability of not getting an ace as connected. So here, if E is picking an ace, if the event E is picking an ace, then its event, respective event E bar or E complement, is not picking an ace in case of this situational problem of playing cards. So E is picking an ace, or an event E bar is not picking an ace, then in this case these two are complementary events. That implies E and E bar are complementary events, and because they are complementary events, I have P of E plus P of E bar is equal to 1, is what we have seen as the mathematical definition. But probability of picking an ace is 1 over 13 plus P of E bar is equal to 1. Therefore, P of E bar can easily be found by taking to the other side, where P of E bar is 1 minus 1 over 13, which on simplification through LCM gives me the answer as 12 over 13. Therefore, I conclude that for the second bit, the probability of not getting an ace when the card is picked from the playing cards, of not getting an ace, is 12 over 13, is what I get as the answer. So this is how we do many situational problems of daily life connected with probability, where we find the chance of happening and not happening. In this case, chance of getting an ace and not getting an ace through the exclusive formulae as discussed in the topic of probability. Now we have seen the playing cards in the previous problem, which pauses us in some of them not knowing on what exactly are the playing cards and its rules and its contents. So to understand the problems, some of the problems which are expected in examination on the playing cards, we need to understand the rules of the playing cards, which is very important to understand the rules, and then we can understand the actual problem asked on probability connecting the playing cards. So let's see exactly randomly on how many contents we have on each of the playing cards. So totally there are 52 cards in the game of playing cards, and these 52 cards are divided into 13, 13, 13 and 13. So each of the 13 have one of them being black diamonds, black spades, and next is red hearts, and next is red diamonds, and the next is black clubs. So you have 4 different types of cards named. One is black spades, which are 13 in number out of 52, and red hearts, which are 13 in number out of 52, and red diamonds, which are 13 in number out of the 52 cards on the whole. And finally, there are 13 black clubs in 52 cards. Usually, the black spades are given with the symbol like this. This is how we have the black spades. And then I have red hearts, which is red in color, and this is black in color. And the red diamond, which is again red in color, and this is black, and clubs. This is how the symbol of the black club is. These two are red in color and these two are black in color. Out of this, the 13 cards, each of the 13 cards are numbered from 1, 2, 3, 4 to 10, and then we have ace, king, queen, and jack. Similarly, I have the numbers 2, 3 till 10 and ace, king, queen, jack for each of the different black clubs. So this is how we have 4 different types of cards with each of them number from 2 to 3, 2 to 10, and ace, king, queen, and jack, and then each of the red hearts and red diamonds and red clubs having the similar number in count with their own symbols as put on the cards, is how we have the total playing cards with each of its contents as given out here. So let's see a problem connecting the multiple events. That is, here I don't take one experiment, but I take more than 2 coins or 2 dice or 2 playing cards and do together at once. To support with this example problem, what is the probability of getting the sum as 7 when 2 dice are rolled at once? That is, I have 2 dice, the dice 1 and the dice 2, which are rolled at once. Now for this, now as I see here that my top surfaces here is 1 and here it is 6, that is 1 plus 6 is 7, is how we find the different possibilities. But before this, I need to know the sample space which is to be identified for this. The sample space for this kind of problem is that for each one on the top surface, there are 6 possibilities here. That is, For every 1 on the first dice, there is either 1 1, 1 2, 1 3, 1 4, 1 5, and 1 6. Similarly, when I have 2 on the top surface, for each 2, I have 6 possibilities here, such that I get 2 1, 2 2, so on and so forth till 2 6. Similarly, for each 3 on the top, I have 6 possibilities for the second dice, such that I get 3 1, 3 2, so on and so forth till 3 6. And each of 4 on the top gives 4 1, 4 2, so on and so forth, 4 6. And each of 5 has 5 6, and each of 6 on the first dice has 6 possibilities, 6 2 till 6 6. Therefore, this is my sample space for each of 1, each of 2, each of 3, each of 4, each of 5, and each of 6 has 6 different possibilities. That is, for 6 different possibilities, there are 6 each individual possibilities. Therefore, my n of s is 6 times of 6, which is 36. Therefore, total number of outcomes when 2 dice are rolled is 36. Similarly, my number of events favorable to event E also needs to be found. Here, the event which I need to identify initially out here is that the event in case of this problem is getting a sum of 7. Getting a sum of 7 is the event identified in this problem. So, getting of a sum of 7 is what we need to find for this. So, let's see what are the different possibilities of getting a sum. Initially, when I have 1 on dice 1, I have 6 on dice 2 is how we get the sum as 7. Similarly, for 2, I have 5 on the second dice, which gives sum 7. For 3 on the first die, I have 4 on the second dice, which gives me the sum as 7. Therefore, 4 on here gives me 3, and 5 on here gives me 2, and 6 here gives me 1. So totally there are 1, 2, 3, 4, 5, 6 possibilities through which I can get the number of outcomes favorable to getting a sum of 7, that is event E, is 6. Therefore, my n of E is 6 and n of S is 36. That implies probability of getting a sum of 7 is n of E by n of S. Using the formula, I get 6 over 36. That is 6 1s, 6 6, 1 over 6 is the answer. Is how we get for multiple events. In this case of an example problem, 2 dice are rolled at once. Is how we identify the given problem through the sample space and the events possibility of getting a sum of 7 connected to multiple events. So now that we have completed the topic of probability, now comes the limitations which we are going to discuss in its own probability. So probability has its own limitations. Initially, to start with, we have seen that for an event E, the limitations of the probability are that P of E always lies between 0 and 1. So we have already identified this using the mathematical definitions. And also we have seen that sum of all elementary events is 1, or sum of all probabilities is equal to 1. But if imagine I take, say, I have different balls in this bag where one of that is big and the small balls are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are one big ball and 15 small balls. Then if I apply my probability to these kind of problems, then I think I have to search for my own limitations in defining the probability, because in case of this bag containing one big ball and 15 small balls, If I say, what is the probability of picking the red ball from a bag containing one big huge ball and very tiny small balls, then it is easy to remove the big ball randomly taken out of the bag. So we cannot expect any probability or a chance here because the event is said to be certain in case of this exclusive example problem. So this kind of an example problem makes us understand on rethinking on how we limit the defining of a probability. So in this case, it is a certain event. We see that probability of picking a big ball is certain. But this is an absurd to the definition of probability because any by ns doesn't give this to be correct answer. So in general, if I take picking up a big ball is certain, but this has its own limitation. So let's see what is the limitation. Probability cannot be applied to this kind of a problem because probability cannot be applied if each of the events are not equally likely to happen is one of the biggest question in probability and its limitations. Because when I define probability, I need to identify that each of the event has to be equally likely to happen. In this case, it fails because happening of each of the small balls, picking up all the small balls in the bag is equally likely with each of the individual small ball, but when compared with the big ball is not equally likely to happen in comparison to the smaller balls. Therefore, for probability to be applied, I need each of the balls or to be picked where each of them should be of same size, which is called equally likely to happen and equally likely not to happen, is how we understand the limitations of probability connected with mathematics. So usually in many of the problems, we have identified the word random selection, that is, a ball is picked randomly. So what do you mean by the word random in mathematics or in probability? This plays a very important role in random selection because for any probability to happen in its trueness, we need to randomly select. Say for example, I have a bag containing full of balls. I randomly pick one of the ball, but I don't have any other rules or the smartness or the cheating which I apply in picking up a ball. So random selection plays a vital role in probability or calculation of probability. So whether I pick a card or whether I toss a coin or whether I pick a ball from the bag or pick a card from the playing cards, I randomly select the card from the playing cards or I randomly pick the ball from the bag containing different balls. So random selection is very important in restricting to understanding of probability through limitations. The word random selection is applied in every problem. This is how we understand random selection. So the next limitation we are going to see in probability is about biased and unbiased coins. Very frequently we see in many of the problems where it says an unbiased dice or an unbiased coin, etc. So what is unbiased or what is biased? How do we differentiate? And why is it that is so important to refer in the problem that an unbiased coin is tossed for expecting the probability? So what is the reason is what is the biggest limitation in probability. So let's see how we differentiate between biased and unbiased and its importance in the existence of probability. So to start with, let me differentiate between unbiased and biased, say referring to the coin or a dice or any other object which is taken in the event E of the probability. So when I take the unbiased and biased coin, say for example, this is referred to be equal chances of landing on each face. So an unbiased coin or an unbiased dice is referred as that coin or a dice in which each of the face has equal chances of landing. For example, I take a coin and I would like to toss. Then my heads should have equal chances of landing and my tails should have equal chances of landing on either side of heads and tails. So let me take this example of an unbiased coin with a coin out here. Now with this coin, when I toss, I may get a head or a tail is based totally on how realistic I am in using this coin. When I say unbiased coin, I see that my equal chances of landing either on heads or on tails is equally with same chances. But mathematicians or sometimes critics always say that some coins are unfair when used in tossing of a coin or expecting probability to that. So that unfair chances are called biased coins. So in probability, we always take equal or fair chances of landing on each side, that is unbiased coins or unbiased dice, etc. So therefore, in this case, this is set unequal chances of landing. Therefore, this is called unfair coin, where one side might be bulged or raised or the other side might be flat. This is how we differentiate between biased coins and unbiased coins. So in probability, it is very important to decide on whether a chosen coin or a chosen dice is biased or unbiased. If biased, we don't take this into consideration. If this is unbiased coin, we take that into consideration. Say this is an unbiased coin. An unbiased coin is this.